So, today we will be discussing the topic compaction that we have already discussed in a few classes, and then we will be moving on to the next topic, that is the compressibility. We have already discussed a few properties, the few effects of compaction on the engineering properties, that is the structure and the permeability. How does it change when the compaction is there at different compactive efforts and at different water contents. Now, see here, when you talk about this water deficiency, you know, water deficient, that is water is somewhat less. How at you can easily by common sense also you can say that the water deficiency will be there on the dry side, because if we say this is the curve here and this is the OMC, let us say OMC, optimum moisture content. So, what happens in the dry side, the water will be slightly lesser because water content is less. So, deficiency of the water on dry of optimum is found to be comparatively on the more here, because deficiency means more, which one is more less. So, on the dry of optimum the deficiency will be slightly more than on the case on wet of optimum. So, we can easily say this point. Then moving on to the second, this fourth point, that is the pore water pressure, second topic of the day here. Due to the high deficiency of water on the dry of optimum, what happens? The pore water pressure will also be less because the water is less. So, the pore water pressure that it will be applying, that will also be slightly less. And what happens in some cases, the pore water pressure on the dry of optimum is observed to be negative. So, what is there, the value is slightly less, it tends to be slightly lesser, and this water deficiency affects the pore water pressure also. So, you can see the water is more deficient on the dry of optimum because the water content is slightly less, and when we talk about wet of optimum, the water deficiency is not as much as in the case of dry of optimum. When we talk about the PWT, I have used a short form here, that is the pore water pressure, and this is the dry of optimum, it is less, and for wet of optimum it is slightly more, because the water will be more here in this point. So, water will be more, so the pore water pressure that it will be applied in the soil, it will be slightly more. When we talk about shrinkage, now what do we understand by shrinkage? That whenever we dry something, what happens? Shrinkage takes place. So, first of all understand that if we take let us say flocculent structure, what happens? It is somewhat made up here, these are a few particles. Now, this is linked up, this is joined by this and this is joined by this. So, this kind of structure is there. When this kind of structure is there, what happens? There is some reactive restraint that is available. Let us say if some load is applied here, what happens? This structure will try to resist the load. But if we say the structure is like this dispersed structure that we have already studied and discussed when we talk about the clay structure. So, if in this, what happens? If the load is applied here, so the shrinkage which will be observed, that will be more shrinkage, but here because of the reactive restraints, because when the force is applied, this structure will not try to collapse at first, and then this structure will try to force up the put a reaction above the for the this load, and so due to the reactive restraints available in the soil, what happens? The shrinkage which will be observed, that will be slightly much lesser. So, we have talked about the shrinkage here. And when it is dried, what happens? The soil which is compacted on the wet of optimum, it tends to show more and more shrinkage. So, see here, shrinkage on the dry of optimum is found to be comparatively less, and on the wet of optimum due to availability of reactive strains, because when you apply the load, the flocculated structure will try to tend to more and more restrain the put more and more reaction there due to the stronger interparticle bridging. Now, obvious one thing is more thing here, that when the soil moisture is more, when the water is more, what happens? When you dry it, then it will try to shrink also more, because anything whichever is there, the things are there, anything will try to dry more if the water is more. If the water is less, then the shrinkage will also be slightly lesser. So, we can see that on the dry of optimum, when the water is less, shrinkage will also be less. But when we talk about wet of optimum, that is water content is more, and we try to reduce the water content, what happens? Shrinkage observed will be slightly more, and the swelling will be just opposite case, as just opposite of the shrinkage. So when the high deficiency of water is there on the dry of optimum, the higher swelling pressure is available there. So as a result, the swelling pressure here will be more on the dry of optimum than on the wet of optimum. So shrinkage is just opposite to swelling. Now understand the compressibility. When we talk about the compressibility, we will be discussing here at, there are two cases, at low stresses, at higher stresses. Now see, when where the soil structure on the dry of optimum is intact, see here, when this is the case, what happens? The soil is trying to restrain something, and but if this P load is slightly much lesser, what happens? This structure here will try to restrain more and more. It will try to restrain. It will not try to collapse here. But if the P load is more and it tries to break the structure, and if this structure collapses, if this structure and the reactive restraints collapses, what happens? The soil will tend to, we will be discussing the other case, that is the higher stresses case. Now see here, what happens in the low stresses, when the where the structure of the soil on dry of optimum is intact, because the load that is provided is what? Slightly much lesser, and the reactive strains that is providing is holding the structure intact, that is, it is not breaking. So the compressibility is found to be comparatively less due to stronger interparticle bridging. But at high stresses, what happened? When the load is increased, what happens? The structure will be collapsing. So when the structure on the dry of optimum is broken, that when I showed you that if the load is slightly increased, then in the case of the low stresses, what will happen? The structure will collapse, that is, the structure will be broken. The compressibility will found to be comparatively more. So see here, at low stresses on the dry of optimum it is less value, and on wet of optimum it is slightly more value. But when you talk of high stresses, what happens? The structure is broken. So in that case, on the dry of optimum the compressibility will be more, and on the wet of optimum the compressibility will be lesser. Now if we talk about the strength, due to stronger interparticle bridging, the strength on the dry of optimum is found to be comparatively more than on wet of optimum. So you can see here the strength is more, the stress, and if you talk about the strain, so the strain which is reached, so the changes that are made in the strain, that is slightly lesser, but if you are talking about the wet side, it is slightly more. And also understand, if we talk about the dry side here, so it is more brittle, and if we talk about the wet of optimum side, that is more than the on the, and we plot the graph there, so it comes out to be more ductile. It will try to resist more and more stresses, and brittle collapse and ductile collapse, you already know this thing. So I have simply arranged this, the entire thing that we have studied. So structure, flocculent and dispersed, permeability on dry of optimum was slightly more, and on wet of optimum it was slightly less. When we talk about water deficiency, what was there? Water is more deficient on dry of optimum, so it is there more, and on wet of optimum water is already present, so water deficiency will be slightly lesser, so it is less. When you talk about the pore water pressure, it is dependent on the water. पानी जितना ज़्यादा होगा उतना ज़्यादा पोर वाटर प्रेशर वो एक्सर्ट करने की कोशिश करेगा. So on the dry of optimum the water content is less, and similarly that is the water deficiency is more, and so the pore water pressure will be lesser. Now if you talk about the shrinkage and swelling characteristics, you can always say that when the water content is more, so when the shrinkage will be there, when you dry the soil, what happens? The soil will try to shrink, वो थोड़ा सा सिकुड़ना स्टार्ट कर देगी. तो जब पानी ज़्यादा रहेगा तो वहाँ पे श्रिंकेज भी ज़्यादा ऑब्जर्व किया जाएगा. बट व्हेन वी टॉक अबाउट द ड्राई ऑफ ऑप्टिमम, व्हाट हैपेंस देयर? द श्रिंकेज विल बी स्लाइटली लेसर, एंड द ऑपोजिट विल बी देयर केस इन स्वेलिंग. And we talk about compressibility, we have discussed the two cases, that is the low stress and the high stresses. At high stresses the structure of the soil gets broken down, and then the compressibility will be slightly more. in this case. When we talk about the strength, it is obviously slightly more when we are talking about the dry of optimum, and when we talk about the wet of optimum, the strength is slightly less as compared to dry of optimum. Now, where can you use these things? That when we talk about the core of an earthen dam, there you are using the wet of optimum thing, where that is you are compacting on the wet of optimum, because you have to reduce the permeability. That is, see here, you know that when we are talking about the permeability, see this point here. So, on the wet of optimum the permeability is less, and in an earthen dam you try to reduce the seepage there. So, to reduce the permeability and prevent the cracking in the core, you use this thing. So, you compact on wet of optimum. Now, see this here, subgrade of pavement. What is there? It is wet of optimum. Why it is done on the wet of optimum? To limit the volume changes, because on the dry side it is not such the case. And if you talk about this homogeneous earthen dam, it is compacted on the dry of optimum, because the strength, see the strength here, it is slightly more on the dry side. So, to have a stronger soil and to prevent build-up of high pore water pressure. Now, see if we talk about the pore water pressure, what happens there? When we talk about the dry of optimum side, it is slightly lesser. If the pore water pressure is lesser, so that will be putting somewhat less pressure when we are talking about the homogeneous earthen dam on the structure. So, that is why we do the compaction on the dry of optimum. So, you take upon the different values on the wet of optimum or the dry of optimum, and similarly compact the soil. Now, these are the few, we already studied the Proctor needle test, wherein you find out the water content and you calibrated that thing, and then we moved on to the compaction curve there. Then field compaction control is done by vibroflotation technique, and by pounding, and then by explosive. So, these are the few methods in where you do the compaction in the field. Now, moving on to the new topic here, we will talking about the compressibility, then we will move on to the consolidation. So, what is compressibility? First of all, it is the process of decrease in the volume of soil. Let us say if the volume of soil was somewhat this, now the volume has somewhat decreased. This is the volume V and it has changed to V dash. So, the volume has somewhat decreased here. In this case, what is there? Due to anything, I have given you some example here that the volume of soil can be decreased due to increase in the load, let us say the first thing, load or the effective stress over it, and it is also influenced by the soil type, whatever the type of soil, and its structure, the geological origin of the soil that we will be discussing how it is there, and then its stress history, because soil has some memory. I will tell you one example there when we talk about the stress history. Now, as the soil is assumed to be semi-infinite, entire changes in the soil is represented as a change in depth of soil, that is one dimensional compression is being considered. So, very important thing here, understand that when we are talking about semi-infinite thing, understand we are taking, let us say this is the ground surface here. So, this area we have considered as infinite, this area, this ground area, you are seeing the cross section here, this ground area is considered to be infinite. So, what happens here, when we are talking about some load is being applied on the soil, there will be some compressibility, there will be some volume change, the soil will try to what? Reduce in volume, and what happens there, let us say if the volume gets reduced like this, the new ground surface is this here. So, what happens, this cannot be represented in when we try to say that the area is infinite. So, we cannot represent the volume in that terms, but we can say that the volume change which has occurred can be also said in terms of height, ki this delta H has been reduced, the earlier volume was somewhat more and now the height has somewhat reduced here. So, that is the delta H value. Now, understand, let us take a case wherein the soil is what? Not semi infinite. So, what would have been happened here, let us say if this is the let us say soil and you put in the load here. So, what will be the condition here? Now this soil will try to bulge from the sides. If the base is, let us say, rigid, if the base is rigid and there is no movement here, so what will the soil? The soil will try to what? Somewhat reduce in the height. Let us say if this is got reduced in the height, and also what will happen? The force will be transmitted along the sides also. So the soil will, which was originally this thing, now will be expanded to this much portion here, this portion. So the volume, the height has also reduced and the sides have also expanded. So this is the case wherein you are considering the total finite dimensions. But when we are talking about the infinite dimensions, at that point of time the volume change can be simply represented in terms of the depth, because the area is there infinite. But if we talk about the area being finite, then this will be the case wherein you have to analyze the bulging also. So this is not the case eventually that we will be considering. We will be considering all the semi infinite cases. Now understand one more thing, that compressibility of the soil is due to the following 4 factors. Now what are these 4 factors here? First of all, whenever when we talk about the compressibility, always keep in mind that the volume is being changed, that whatever be the some initial volume say, now that volume will be getting somewhat reduced. Now what is the reason for this volume reduction? There can be 4 reasons. Now first of all, the expulsion of air or compression of air in the voids of soil. You already know that if this is the soil, what happens? This is the, let us say, solid portion, and then this is the somewhat water portion, and then this is air portion. If we are doing it, then what are the methods that you can apply? You can apply the compaction method. So when you compact the soil, what happens? The air is removed from the soil. Okay, and that process we have already discussed in the entire previous 3-4 lectures, that the compaction is taking place, or the expulsion of air is taking place, or the compression of the air in the voids of the soil is taking place. Now what happens to the water there? So when the air is expelled, what happens? When the air is present, first case see here, when the air is present, what happens? The saturation value is between 0 and 1, but as soon as the water goes out, the volume gets reduced. Now the voids contain what? Only and only water here. Voids will be containing what? Only and only water. Now this water will have to be removed. So when the water is removed from the voids of the soil, it is termed as 1 degree consolidation. Okay. Now the third thing here, what will happen? The compression of soil solids and the water, which is generally neglected. Now see, the soil solids and the water are by nature compressible. But when we are talking about the assumptions that we have assumed, we are considering that these soil solids and water are incompressible. Though they are compressible, but they are having compressibility value slightly so much less that we can simply neglect them. Now the fourth thing is there, that is the plastic. When these 3 processes, the first thing is compaction, then the 1 degree consolidation, then what happens? The compression of soil solids and water takes place. Then after that there is plastic readjustment of soil solids, that is the 2 degree consolidation. So the soil solids will try to adjust in terms of plastic readjustment. What is plastic readjustment? That is the adjustment of the soil solids without undergoing rupture. So that is the 2 degree consolidation, and this 2 degree consolidation will take a lot of years, much time as compared to 1 degree consolidation or compaction. Compaction is a natural process and 1 degree consolidation is a compaction is a mechanical process and 1 degree consolidation is a natural process. So we have already studied the difference between these 2 things. So this 1 degree consolidation and 2 degree consolidation comprise of the entire consolidation, that is the settlement of the soil which will be taking place. So मिट्टी कितनी ज़्यादा धस जाती है वो किससे डिपेंड करेगा? कंसोलिडेशन से. अगर हम कॉम्पैक्शन करते हैं, सो वी आर ट्राइंग टू मॉडिफाई द अमाउंट ऑफ the settlement, that we are trying to make the soil more and more stable. So that is the compaction portion. And now if we talk about the 1 degree consolidation, we will be discussing another thing, and 2 degree consolidation we will be discussing some other portion. Now Now first of all, before entering into the topic of consolidation, we will be discussing by a spring analogy that has been given there, wherein we consider a cylinder here. See the cylinder in this point, this is the cylinder, and in this cylinder what happens, the valve is provided, okay, and this is the water that has been inserted in the cylinder. Also understand one more thing, that there is load placing space that is being given, so the load can be placed in this portion, and then there is a spring attached to it. When the load is placed on this portion, what will happen, the load will trying to compress the spring here, and initially in the first two cases, in the very first figure and the second figure, the valve is kept closed, but thereon what happens, we will be opening the valve here, and in this fourth case. So these are the four cases, that four things that we will be studying here, four different stages that we will be studying. So let us say initially the valve is closed in the very first case, and there is no load being placed here. So the initial stage is like this, the spring is initially uncompressed, the water is being here in the container, and the pore water pressure is, the change in pore water pressure delta U, that is equal to 0. Initially there is no effect on water. Now what happens, if you place a load here, so initially when the load is placed, because the water is what is there, so the water will try to take up the entire load here, okay. When the water takes up the entire load, what will happen, there will be change in pore water pressure, so delta U comes out to be P by A. Now what is P? P is the load that is being applied, and A is the cross sectional area. A is the cross sectional area over which the P is being applied. So this P by A is the change that has been provided by this P, by this load P, that is the stress that has been induced by this load. Now still the valve is closed, because the valve is closed, so the water cannot move out. As the water cannot move out, so the water will be trying to take up the entire load, that is this P, and it will prevent the soil, this spring to take up any load. Now see, if we open the load, what happens, the water will get a space and the water will try to move out. So see the third figure here, if we open the valve, what happens, the water here will be trying to move out of this valve, and what happens, the spring will come into action, and this will get slightly compressed, and the pore water pressure, pore water pressure is nothing but what, water taking up the pressure, and initially there was the entire load was taken up by the water, but now what happens, some part of that load P is taken up by the water, and some part of the load is being taken up by the spring there. So now understand here one more thing, that the pore water pressure here, the pore water pressure will be slightly much lesser than P by A, because whatever be the reduction, earlier it was P by A, now whatever the value has been reduced here, so this value, whatever be the value has been reduced, that subtracted value will be moving on to what, that load would have been taken care of by the spring there. So now which the entire load was with the water, now that load has been distributed with between the water and the spring there. Now if you move on to the fourth case here, what happens, till the water is trying to push up the soil, what happens there, the water here will try to move out, but at some point of time the pore water pressure will be 0. When the pore water pressure reduces to 0, what happens, the water will be stopped, there will be no outflow of water from the valve, because this water is not trying to push any go out any further. So the pore water pressure reduces to 0, and the entire, now what does this denote, what does this is the pressure gauge which is there in all the four figures, that is representing the entire load or the stress that is being taken up by the spring or the water, and that is the water. Now what happens, in this figure entire load was taken up by, there was no load, and water and spring were initially present, but what happened in the next stage, the P load was taken up by the water. By why this happened, and nothing by spring, because the valve was closed and water initially took up the entire load there. But as soon as we opened the valve here, see, as soon as we opened the valve here, water got some space, and whatever the pressure it was exerting, now it got relieved, because the water which was under pressure, it just got an opening. So through the valve the water moved out, and now the water pressure also reduced, and also the spring which was not taking up the load till this point, now spring will also be taking up some load, and the remaining portion of the this load is already taken up by the water. Now slowly what happens, the water will dissipate out all its energy, all the pressure that it was taking. So the water pressure now reduces to 0, and as the water pressure reduces to 0, this is the water pressure, let us say, that is the delta U, that is this, when this point reduces to 0, what happens there, the entire load will now be taken care of by the spring. And so now in this stage there was water that was taking up the load, in this stage there was solid, and that is a spring and the water that was taking up the load, and eventually all the load will be taken care of by the spring itself. So in this thing you have to understand that this spring here acts as what, as the soil solids, and the water is already present here in this is the water that has been present. So how the load gets distributed we have studied, and you have understood this entire phenomena. Now for this thing we will be discussing further when we discuss the different steps, and this is nothing that is new here, but simply the representation of that entire figure. So this point we will be discussing in the next class, and we will just go up into the consolidation part. Thank you.